All right, so part one of getting ready for the AP chemistry exam. All right, so what we have, we're going to talk a little bit about atomic structure. What we have is, we're going to talk about lithium. Now, lithium, that is a metal, and we're going to come back to talk about what metals are, etc. But lithium has an atomic number of 3. You find that on a periodic table. Lithium has an atomic number of 3. What that means is it's going to have 3 protons and 3 electrons. Now, in an atom, those protons are located in the nucleus. We've got 3 protons located in the nucleus, and we're gonna have 3 electrons, 2 in the first, 1 in the second, energy level. Now, why does it have a structure like this? What are some fundamental ideas that we need to kind of keep together here? Well, one of those fundamental ideas that we're gonna have is this idea of electrostatic forces. And that is that opposite charges, they're going to attract, and like charges, they are going to repel. This is a fundamental thing that you guys need to keep in your head the entire time we do chemistry. This is why bonds get created. This is why intermolecular forces do what they do. This is why atomic structure has trends. It's this idea that like charges are going to repel each other and opposite charges are going to attract. Now we come back over here to lithium. We have ourselves an electron here, an electron here, being attracted to the positive. That's favored. That's something that it's going to happen. These electrons are going to get attracted to their protons here. But then why don't we have, and we want to make those as much as possible. We want to get those positive and negative charges as close to each other as possible. We want to maximize attractions. We want to maximize the attractions, but we want to minimize the repulsions. So keeping with the idea that opposites attract and like charges repel, we don't really need protons, and like charges repel, what we have is we've got these electrons being pulled as close as they can to the center while staying away from each other, and we can't fit a third electron inside of here because what that ends up causing is it causes too much repulsions. So we want to maximize attractions and minimize the repulsions, and this just happens to be the setup in which 3 protons and 3 electrons have the most amount of attractive electrostatic attractions taking place while minimizing the repulsions there. Okay. So what we have is we've got lithium. Now, what we do have with lithium is we got 3 protons pulling in on 2 electrons here, and they're pulling them in really, really tightly. Now we've got the same 3 protons pulling in on this 1 electron out here. So these 3 protons are pulling this 1 electron out here. However, these first 2 electrons in this first energy level right here, they're going to provide what we call shielding. They're going to provide shielding. And what that means is that these negative charges are going to take away some of the positive attractive charges between this positive and this negative. And so what we have is, imagine if we have ourselves this guy, and they're pulling in on each other. All right, so they're pulling in on each other. But then imagine over here, a third force comes over and pushes on this guy and pushes on this guy. And so what that does is it takes away some of the net pulling in because these guys are pushing out on this guy. Or imagine spending money. If I sit here and go, oh yeah, I have a job and I make $100 an hour. But in order to have the job, I got to pay $20 to you to have the job. I got to pay $20 to you to have the job. And so I'm really only having a net take home of $60. Well, we say that 3 protons pulling in on 1 electron with 2 pusher outers, so 3 puller inners and 2 pusher outers would have a ZEF, or an effective nuclear charge of 1, which means that those 3 protons, when they pull in, are really only having an effective nuclear charge, only effective charge of 1 pulling that guy in. Now, that's important. It's gonna be very, very important. We're gonna come back to it. So let's hang on to that idea. We're now gonna look at fluorine. We go across, and I'm looking at my periodic table up here. We're gonna go across to fluorine. It's on the same exact row as lithium. And we go across to fluorine. We look at fluorine and we go, oh, it's got 9 protons. It's got 1, 2 energy levels. And by the way, it's on the second row. That tells you how many energy levels we have. We've got 2 in the first, and then 1, 2, 3, 4, 5, 6, 7 electrons in the outermost shell. So we have 9 electrons total. All right, so 2 plus 7 is 9. And we've done some fundamental atoms. We don't need to go through 2 and 8 and all that good stuff. Now, we look at this. Ask yourself, what is the effective nuclear charge of fluorine? And this is fluorine, by the way. Well, you say, I've got 9 polar inners. I've got 2 shielders, so 2 pusher-outers. So this valence shell here, remember that's the outermost shell, it's called the valence shell. This valence shell will have a ZEF, an effective nuclear charge, of 7. And you go, okay, so what does it matter? Who cares? What does all this actually mean? What this means is that this electron here, let's go ahead and just put this guy on the other side, and this electron here, both of them are being pulled in. But this guy is not being pulled in very well compared to this guy. So imagine if something comes by, a positive charge comes by, and this positive charge says, hey, I'm a positive charge, you're a negative charge, I'm a positive charge, you're a negative charge. I'm going to attract you to me and possibly pull you away. I'm going to pull you off of this atom and make you mine. I'm going to pull you off, negative charge, and make you mine. Well, what happens? This guy has got to overcome a ZEF, an effective nuclear charge of 1. So it's not got to put a lot of energy in. This guy is going to have to overcome his effective nuclear charge of 7, which means it's going to have to put a huge amount of energy in. It's this huge amount of energy to pull this electron away. And you go, well, what does that matter? Who cares? Well, this will possibly reach the energy required to ionize this lithium. That's what we say. We're going to ionize this lithium. An ion is a charged atom. We're going to remove this electron away. This positive charge says, oh, I only have to put in this amount of energy, and I can reach that amount of energy to pull you away. This guy says, there's no way. I've got to overcome huge amounts of energy, giant amounts of energy to pull this electron away. There's no way I can reach that. But if I find another lithium, hey, I can do that. That's easy, no big deal. So what happens? We say that this guy has a relatively low ionization energy. We would say this guy has a high ionization energy. And on top of that, we would say that this guy, this lithium here, will behave as a metal. And this guy will behave as a non-metal. What does that mean? The definition of a metal, period. The definition of metal, not that it's lustrous, not that it's shiny, none of that stuff. The definition of a metal is that the energy required to remove an electron is reachable. And it happens, and it will happen. A metal is an element that has a tendency to have its electrons removed away from it. And don't say just loses electrons. No, those electrons will be pulled off somehow. So a metal has low enough ionization energy where something comes by, it's able to pull those electrons off. So it has a tendency to have its electrons removed. What's the definition of a non-metal? The definition of a fluorine, a non-metal? Well, its energy is high enough to not have its energy reached, to not be ionization, the ionization energy reached. And so it holds on to its electrons. So what does that mean? we come over the periodic table. And what do we see? As you go across the periodic table, the Zephs are going to get bigger and bigger and bigger. And so what's going to happen is this guy has 2 energy levels and has 2 shielders, 3 protons. So it's a Zeph of a 1, a Zeph of a 2, a Zeph of a 3, 4, 5, 6, 7, 8. Ooh, what does that mean? As you go across the periodic table, the ionization energy increases because the number of protons in the center increases, but the number of shielders stay the same. They all have 2, but increasing the number of protons pulling in, polarities go up. So the energy required goes up. And so as you go across, the ionization energy increases and they behave more as a non-metal, And so this is why this side of the periodic table we say are metals, and this side of the table they behave as non-metals. And that explains why noble gases have a tendency to be not very reactive. Why do they not be very reactive? Because their ionization energy is so big. It's so big that things are not able to come along for the most part and be able to take those electrons away or even share electrons with them until we get down here. Why is it as you go down the periodic table does the ionization energy decrease? Why does the ionization energy decrease as you go down? Well, we come back to this. We look at lithium. Lithium's got 3 protons, 2 shielders. So as a Zeph of a 1, we go to sodium. Sodium, almost done, hang in there. Sodium's got 11 protons. Sodium's got 1, 2, 3 shells, 2 electrons in the middle. 1, 2, 3, 4, 5, 6, 7, 8 in the second energy level. And then we have 1 out here. What do we have? We've got 11 protons pulling in. We've got 10 shielding electrons, 10 pusher-outers. So we still have a Zeph of a 1. They have the same Zeph, but guess what? Sodium's more reactive. Sodium's ionization energy is even lower. And why is that? Because the distance is farther. So imagine I have a heater. That heater's sitting right here. I'm able to feel the heat from it. It's not very strong, but I'm able to feel the heat from it. Would it make sense that as this moves away from me, the heat that I feel, the energy I feel from that energy source is going to go down? Same thing here. As this electron moves away, the energy, the electrostatic attraction is going to go down. It's what we call Coulomb's law. In Coulomb's law, we say that the force of attraction is equal to, there's a constant here, Q1, Q2, those are the charges, +1, -1, etc., over radius squared. We say that as the radius increases, this force of attraction is going to go down. It's in the denominator. The bigger the number the denominator is, the smaller the force of attraction is going to go down, and vice versa. The closer it is, the smaller the radius, the force of attraction goes up. Okay, so that was a quick review. I'm not going into crazy details here. I'm not trying to teach you for the first time. Basic atomic structure, effective nuclear charge, ionization energy, electrostatic attractions, Coulomb's law, metal, non-metal.